So thank you for coming after the coffee break. That means the coffee break was not the reason of your arrival here. So, and I'm glad to present Professor Achyutha Krishnamoorthy from Kerala. So, just a few words. Kerala and Karelia sound very similar. We have many similarities there. So, the nature is very rich in Kerala. The climate is... yeah, it's pretty much the same. I mean, in terms of stability, in Kerala it's very stable. It's something like plus 30 degrees. In Karelia it's also very stable time to time, so it's something like about 0 degrees every time, in summer and in winter, whatever. So, but also there are some similarities, but Kerala is also a very rich region in terms of nature, in terms of culture. It's very diverse. And it's also rich with very generous people. And Professor Krishnamoorthy has taken on this effort.
Lakes, in fact. Lakes, that's the main point. Lakes.
Lakes, and that lakes are also, we say that Karelia is a land of lakes, but Kerala is also a land of lakes in India. It's the southwest part of India. So, and Professor Krishnamoorthy and his team, his dear esteemed colleagues, they also take all the effort to come here. And I thank them once again for this, because it's really a large journey on that point. And so Professor Krishnamoorthy will give a traditional form of lecture. So it will be given by this, pen and whiteboard. So thank you, please.
Thanks, Professor Alex, for this invitation to the team from India to visit here. And for more so, in fact, I was eagerly looking forward to meeting him again. It's a really wonderful place. Of course, the good jacket, I find it difficult because our minimum temperature is never less than 20 degrees, and the maximum it may go up to 35. Before I start this, of course I should thank the Vice Director of this institution again for this invitation and organizing this program. Before starting this presentation, I should just mention a program that my colleague Dr. Joshua is going to organize at this institution. It is one of the oldest institutions, if not the oldest, in India. Established by the Church Mission Society, Church Mission South India, in 1817. That's the year in which the college was established. Now, it has just completed 200 years of its existence. And I'm an alumni of that institution. So after my retirement I was working with the Cochin University of Science and Technology for over 31 years, and the retirement, and even after post-retirement, I was again engaged with the institution in various capacities, like professor emeritus and emeritus scientist. Currently, I work as UGC, University Grants Commission of India, the emeritus fellow of that University Grants Commission of India at the CMS college where Dr. Joshua is currently working. And he is organizing a program in January 2019, that is next year. Hardly now 4 months left for the program to start. It is on a general topic in the sense that it's applied probability and stochastic processes. Several researchers have already agreed to come over there, lectures, including Professor S.R.S. Varadhan. I don't know how many of you have heard about him. He is perhaps the propounder of the larger deviation theory. He has contributed enormously to stochastic calculus. He is currently with the Current Institute of mathematical sciences at New York University. Incidentally, I should also mention that he was a Nobel laureate for the year 2007. Nobel Prize is the Nobel Prize in mathematics. Perhaps you are aware of that fact. So, and then there are several analysts. Professor Reinover will also be there, and Dr. Alex is just trying to find out whether he will be able to make it, because that is the just a Christmas time in Russia. But then we could not find a suitable time. That's why it is fixed for scheduled for 7 to 10 of January. And he wants to, Dr. Joshua wants me to extend that invitation to all of you. Perhaps Professor Moroso will be able to make it, I hope, from here, if not anybody else other than Dr. Alex. So let's start about the introduction. The hospitality here is really wonderful. Dr. Alex did not allow us to keep our mouth shut for even a single minute. He could not make forcing us to eat. Okay, in this climate it may be okay, but back in Kerala, that warm weather, you can't eat that. You have to drink a lot of water. That's that. Basic difference. Okay, what I'm going to now do is something probably too simple, like what Professor Reinover has presented. I start with the Markov chain. Simple Markov chain. And I will just go to the phase tape distribution. There are some first order Markov chain. Then I want to extend it to phase tape distribution generated by higher order Markov chain. So far, nobody has looked at that aspect. I have not brought any computational result with me. I thought I was very near the result, but then I found that it is far away. In the great epic Ramayana, there is an incident. I don't remember whether I have given a copy of the Ramayana English translation, but it is a very really abridged version. So this is considered to be the first classic in the world, written by a great seer. This describes the story of Rama. Rama is brother Lakshmana and Rama's wife Sita. They go to the forest because his father, who was the ruler of the kingdom, he wanted them to go for 14 years in the forest just to kill a demon. And the demon wanted to steal, or rather kidnap, Rama's wife. He did not know what exactly the way of doing, but then he approached a relative of him. But we call him Marija. Marija, that is something like a mirage. When you are in the desert, you see that there is water, but when you go near that, there is no water. Something like a mirage. So this Marija was asked to take the form of a golden deer, and then attract Rama's wife. So this Marija, in the guise of a golden deer, goes to the hermitage. Sita was attracted by this golden color of the deer. So she requests Rama to grab that. So Rama proceeds, requesting Lakshmana to take care of Sita. What happens? In the process of grabbing Marija, now Rama thinks, oh, he is very near, that deer is very near. The moment he reaches there, this runs away. So he was not able to actually get it. So just like that, I thought that the second order Markov chain, with the second order Markov chain, I can easily calculate the phase tape distribution. Partially I succeeded, but then still I am not near. Everything, then I was thinking that I was near, I was far away. Just like the story of this grabbing auditor. Anyway, so with that brief introduction, we'll start this presentation. Professor Raino will talk about Markov decision, semi-Markov decision, and essentially semi-Markov decision also comes into picture. Not in the, it is in a disguised form. Okay, let's start with a prisoner's problem. It's a simple Markov chain. I'll assume that we have a prison with a number of cells. I'll just take a particular case of, because that is easy to explain. Probably you are already familiar with this, but I'll assume that these are some passages to the adjoining cells. So the prisoner, assume that is, I'll just label them 1, 2, 3 up to 9. And then, since I'm going to describe it as Markov chain, the prisoner stays here for 1 unit of time. He does not know whether there is a way to escape, but of course, because it is closed, and he cannot therefore escape. And I will consider the case of escaping from this by just keeping an opening somewhere, or in all the cells except this one. Okay, suppose he starts from here, stays here for 1 unit of time. For the time being, it is taken as 1 unit of time. Then can go to one of the neighboring cells through the opening. So assume that this is a uniform probability in the sense that he can either go here or go here with the probability half each, because there are only 2 openings. So he can come to 4 with the probability half to 2 with the probability half after staying here 1 unit. If he is here, he can go here or here or here after stay here for 1 unit of time with the probability 1 by 3, assuming that is uniform. And then from here, fine, he can go here or here, here or here. So since there are 4 openings, so he can, with the probability 1 by 4, go to, say, here. With the probability 1 by 4 here, and again, same probability here or finally here. But I assume that he does not say that. Only from some other cells where we can again come back to that cell. So it is after a number of transitions that he will be finally moving that. So this is what is happening, and therefore we have a first order Markov chain, and I have to have, in order that a Markov chain is completely described, first order Markov chain I again stress, because I would like to pass on to second order Markov chain. So this is these are the state elements of the state space. And I can then write here, so going up to 9. So now there is an initial probability vector, because for describing any first order Markov chain, you need an initial probability vector. Then only you will be able to know the position after, say, k units of time, position of that prisoner after k units of time. Suppose I designate by x0 the initial position. So it can be any x0 can be any one. You can assume uniform probability, for example, 1 by 9 each. So initial probability vector can be chosen like this, or you can just go for something more general in the sense, okay, keep it as alpha 1, alpha 2, alpha 9. So this together with this one-step transition probability will describe the Markov chain completely. So I can, with that, just find out the probability of, say, for example, after 10 steps, this position. So this is not a conditional probability, it's going to be unconditional. I want to find out probability of x10 equal to, say, 2. After 10 steps, what is the probability of this being found out? Found in cell 2. Can be calculated. And then, suppose I just give an opening somewhere.
I can either introduce an opening to every cell, say here one, here one, here one. He is escaping now. And the prisoner wants to escape. In this case, okay, what will happen is prisoner can escape except from this to outside. So he goes out of the prison. But suppose he is not able to exactly identify it. So if he is here, well, of course he can either take this passage or this passage to go out. And assuming that there are equal probabilities of choosing these passages, so sometimes we will be just going here, sometimes going here, not escaping. Maybe in the darkness, and therefore he is not able to identify. So then, naturally the question will be, what is the probability of escape? So I can then introduce one more state, say call it 10. So this is a single state, which is what now we can call. Once he is out, he just escapes. And therefore there is no coming back, and therefore this is a absorbing state. And these are what are called transient states. Now I would like to know what is the probability of the prisoner escaping. I assume that initially he is not outside the prison, otherwise he is no more a prisoner. So he is occupying any one of the first 9 states of the transient states. So these are the respective probabilities. And then after 10 steps, he has escaped. Or exactly at the 10th step, he escapes. Now if I want to compute that, again it can be done, assuming that initially, so alpha 10 I assume to be equal to 0. Initially he is not outside the system. Now this I am going to now take to a continuous time arm. What I am going to assume is that instead of staying in a state for 1 unit of time, he stays in a particular state for an exponentially distributed amount of time, depending on the state that he is in and the state he is going to be next one, which is essentially the semi-Markov process that right now we was speaking of. So, in that case, what I will do is, I have a transition probability matrix, but not in every case that will be working out when I try to connect it with the infinitesimal generator. So I'll be a bit careful when writing that. So I have a, yes, P8A, the transition probability matrix. Now this, I'll again take Ij from 1 to 10. But then notice that I can have P10J where J is not equal to 10 equal to 0 whenever J is not equal to 10, because he is out. And also notice that in this case, so for example this cell, which is a 5, I cannot just write P5, 10, this is not equal, this is equal to 0. In one step, the probability of just going out of this, escaping from here, is 0, because there is no direct opening to outside the prison. And therefore this is a 0. This is essentially one step transition problem. And therefore this is equal to 0. Now I am going to, instead of assuming that it is a discrete time unit, I am going to now assume exponentially distributed amount of time in a state. So I will write the parameter as mu sub ij. So he stays in the state I for an exponentially distributed amount of time. So xi is the amount of time it stays. I also write an xij. So let me put it as xij. If he is going to, he chooses j as in state to be visited next then it is exponentially distributed with parameter mu sub I j. Now in certain cases like this, we can just write the following thing, that this is equal to, suppose I just take mu ej is equal to Pij mu. In every case it may not work, but certain cases like this we can just by suitable choice. And then when you work with the continuous time Markov chain, my objective is to find out the time until he escapes. For example, t is a random time, or call it stopping time. What is the probability that once he escapes, okay, he's out. Now what is the probability that it takes at least t units of time to escape? I want to compute this probability. Now what we will do is, or rather if you go for this thing, probability of t less than or equal to t, either way you can just do it. Look at this event or look at this event. Now this one we will try to compute that it takes not less than t units of time to escape. So what I do is introduce a probability. But Alex, are they familiar with this phase state distribution? Students?
No, students are not.
No. Maybe. So if it is not something new, I don't want to just describe that. That's why it's legally asked. So I can continue. Okay. So let me designate by Pjt the probability that the prisoner is currently in state J or the cell J, where J is not equal to 10. Probability of being in cell J. So he is not outside the prisoner. So for this is at time t. At time t. So J equal to 1 to 9 is not equal to 10. J equal to 10 is excluded. And I want to therefore compute the probability that the amount of time he stays in the transient state, set of states, exceeds t. I would like to derive this probability. Assuming that his sojourn time in any transient state is exponentially distributed with parameter mu sub ij. So then how to do that? Alright, as down here, I have this initial probability vector alpha 1 to alpha 9. I take alpha 10 equal to 0 because then he is no more a prisoner. If alpha 10 is taken to be something positive, that probability he is not a prisoner. Now what we will do is just write down the Japan Kolmogravity equations, with which the master students are familiar. I suppose they are familiar with that. So what I do? But if you want to have a sample, I can essentially write down that. So for example, I take a time interval of duration. So kindly keep me informed about the time that I am left with. T plus h interval t. And then, so at time t, I'll just look at the probability that still I am in the transient set of states at time t plus h, given of course that I am in a transient state at time t. So this one possibility is that I was at the transient state j at time t, at that state itself, and then there was no change, which means that I have not moved out of this. So this is 1 minus probability, alright, there is no change during that interval, which would mean that, okay, I can just write it. So mu, what is that, jk, summed with respect to k, from, so j not equal to k not equal to j, that would be more appropriate, k not equal to j, k equal to, in fact it can be from 1 to n except for j equal to k, and of course this is multiplied by h. This is one possibility. And the other possibility is that it was somewhere, it was occupying a state k at time t, and in the remaining interval of duration x, it is just moving to this. So p, this is in fact the probability of, yeah, that's right. I'll just use what is that? Yeah, from k it is going to g, in kg. So some with respect to this possible values of j. So j not equal to k, and can have any value, but other than, of course, it should not be the last one either. Neither k nor equal to k. So then,
I think you lost h small first term, no? First term.
this one?
Yeah.
There is no change.
H.
It is inside. Before the sum.
Before the sum, 1 minus.
Yeah.
1 minus h. It's okay.
Yeah.
No, it's okay. It's okay.
Yeah. Okay. Yeah. This is h. Okay. Yeah. As a short interval of duration. Yeah.
Small and
It was too small and h.
This was small.
Look here or there? Oh.
Okay, thank you.
So then I subtract this from both sides, PJT from both sides. Divide by h, take the limit at h approaches 0. So then what I get on the right side is minus sigma mu j k. K not equal to j. And then multiplied by, of course, the PJT. And then, of course, this PKT multiplied by sigma A not equal to neither K nor N. Because, okay, so instead I could have just written the following form. In it, will come to that. So this is a V, V, okay. Okay, so what happens is that taking this limit as h goes to 0, so what we have on the left hand side is the derivative, time derivative, and this, what happens is either there is a change or this is essentially indicating that it's not going down. Therefore, now since this, what happens when you just write down the coefficients in the matrix form, if I now introduce the vector, say I'll put represent it something like this, probability vector of the system being formed in state, when you know the states, so P1 of E, P2 of E, so on, P9 of E, the transient states, and of course I can write the recurrent state as well, the absorbing state, but then I will just concentrate on this part. So we can from that get the matrix differential equation P prime T equal to a matrix. I'll just write this. The transition from this one, what we get is the following thing, the coefficients on the right hand side if you just take, well this is state 1 to itself, 2, so on. So along the diagonal you can see that this negative sign will be appearing. What I will do is just I'll write, say here mu sub 1 1, indicating this this quantity. For example, now this j not equal to k, therefore the other things added will be giving that mu 1 1. That is therefore it turns out to be negative. What essentially happens is the row sum will be equal to 0. So then here we have mu 1 2, so on 9 here mu 1 9, and so on. Here we have correspond to this. So this is a mu 9 9. You notice from this coefficients that along the diagonal we have non-positive quantities. So mu sub I is non-positive, and mu sub ij for I not equal to j will be non-negative. This is what it means. Now we call this as this part, essentially it is the transient part, the rates of transition, I will call it as t. So this p dash t, this will be turning out to be p of t, where p of t is this matrix and p dash t is the time-wise. So this multiplied by t. With the initial condition, of course, that it's equal to this, I will call it vector alpha. And then, so we have the matrix differential equation given by this with the initial condition P0 equal to alpha bar. I assumed that the prisoner is inside the prison. And therefore, this I have taken as equal to 0, alpha 10 equal to 0. Now, the solution to this is turning out to be, so alpha bar, when you solve it, it's a rather simple equation. So, e power alpha t, or I will write exponential, probably that may be the, alpha bar e power, t multiplied by t. And therefore, this is now a vector, so this is also a vector. And if I want to calculate the probability of, say, these individual components, what I have to do is, to get that, right, multiply by e bar and then get the things. So, the probability is a probability of staying, irrespective of the particular state, transient state that it's in, you will be able to get the probability of remaining still in the present until time t. So, probability of absorption at or prior to time t. So, t is less than t is 1 minus alpha bar exponential t into t multiplied by column vector of 1s. Oh, I'm sorry. Multiplied by a column vector, because this is a scalar 1, whereas this part, this is a vector. Now, in order that, now you get a scalar here, otherwise this is a meaningless part, and therefore multiply by a column vector. So, this vector is standing for a column of 1s of the same order as this one. Only thing is, this is a row vector, whereas this is now a column vector. So, you get a scalar. So, this will be the probability that absorption takes place at or prior to time t. Complement of the other one.
P of t. P of 0. P of 0, P of t.
Oh, sorry, yeah, this is P of t. Yeah, sorry. P of 0 was alpha. Yeah. Thanks. So, P of t. Thanks for talking. Anyway. So, this is what is happening. So, this is for the first order Markov chain. And then, just recollect that I mentioned at some stage I can write like this. But not for every transition probability matrix I can write like that. Certain cases, yes. Certain cases I will not be able to do that. Because what happens is that this condition that the row sum equal to 0 has to be preserved for this what is called infinitesimal generator. I had to have, when I just look at the infinitesimal generator, something more is required. Here, there is something more, which part I have actually noted. This is for the transient part alone. And in fact, for the 10th column 10, there is something like mu sub 110, so on, mu 9. This column vector is there. And then we have this additional row. So this will be from 10, well, it will not go to any of these things. So this stays 0, and since the row sum, well, all these things added together should be equal to 0. Sum of all the elements in each row. Unlike in the transition probability matrix, what we should have is the row sum must be equal to 1. So I will have the row 10 also, here again therefore row 10, and it being absorbing, in the last row we have all elements 0 except the 10th position, and here of course the probability of escape from this, so if this is the only root outside, so 1 by 3 is the probability here, and so on. And of course from 5 you cannot go to 10 directly, that means in one step. The rest of the elements will be described here as the, depending upon the modeling that you are making. Okay, now let's look at whether this form is possible for every transition probability method. So, suppose I just take, I can just written some possible example where it fails, actually we can immediately identify where it does not work. Say for example, I'll take a transition probability matrix, the three-state thing, 1, 2, 3. So state 3 is taken as absorbing. So the transition probability matrix, if I take like this, half, 1 by 4, here again 1 by 4, probability of absorption starting from 1 in one step, absorption to this is 1 by 4. This is 1 by 6, this is 2 by 3, and then this is 1 by 6. Then here 0, 0, 1. Now suppose I take a mu, for example mu equal to 4, and then write this mu equal to 4. Take mu equal to 4, and then try to write the matrix, infinitesimal generator of the whole chain, which would mean, so this is 1, 2, 3. And since for this infinitesimal generator, the row sum has to be equal to 0. Now with the 4, okay, what I get is 4 is the rate of a transition from any state to any other state. So 1, and the probability is given by this thing. So this will be equal to this multiplied by 2, therefore 4. So this is 2, this is what is that, 1, this is cube. So therefore this is just a saying there, therefore I had to write that minus 2, because just remember these are negative elements, or at least not positive. Now 2, what I get is multiplied by 4, so 4 by 6, which is equal to 2 by 3, here again I get 2 by 3, and this is 12 by 3, oh sorry, 8 by 3, will it be working? That's right. Not 8 by 3. Yeah, negative. What is that? I have 4 by 6, 4 by 6. This is going to be 8 by 6, 8 by 3. That may not work. Therefore, so this is a typical case where it will not be working. So what is that? This is. I think I have just written wrong. This is 4. 4 by 3. This is 4 by 3, and then. This is 8. You know, it is okay. So with a negative sign. This one. 0, 0. So what happens? The row sum equal to 0. So this is an infinitesimal generator. Okay? But then, suppose I just go for a mu that is different from 4. And let us see whether it will work for this one. I take a mu equal to 5. No, I think I should change.
Second row is 1 by 3, 1 by 3.
1 by?
1 by 3.
4 by 6?
No, the row sum is not 1.
Row sum?
Here.
No, this is 2 by 6. 1 by 3, sorry. This has to be. That's where I have gone wrong. Okay. So I had to choose that appropriately. What is? If I take 1 by 3, 1 by 3, that should, will it work? 4 by 3?
No, it's not 1. It's 1 over 6, 1 over 6.
Yeah, 4 by 3, 4 by 3, and this is 8 by 3. It will be still okay?
But the row doesn't sum to 1. If you take 1 over 3, you get 1 over 6.
So this is a typical example for where it does not work. Yeah. Yes. True. And therefore this will not be, I'm sorry, I just made a mistake. So this will be minus 4 by 3 with the result that it will not be equal to 0. So you will not be able to necessarily get an infinitesimal generator directly from this number. By just assuming that Bij equal to a constant multiple of, no, this mu ij is a constant multiple of, that is what essentially I wanted to illustrate through the example. Anyway, now what we do is go for
15 minutes.
Huh?
15
minutes. Oh, plenty of time. So sorry, I just made a mistake. But so you have to be very careful not to get from a transition probability matrix. If you want to go to an infinitesimal generator, it may not be very often that easy. Sorry for that mistake. Anyway, so now I go to the second order Markov chain and see how things work. And how can we just look at. So for the first order Markov chain, well, we have derived a phase-type distribution, and the representation for this phase-type distribution, well, this is how it is. Phase-type distribution and then for the particular phase-type distribution that we have derived here, well, it is written as Ph alpha bar. Well, the transient part, we just call this as T, so Ph alpha bar T. There, and call it, this T is of order 9, it's a matrix of order 9, so Ph distribution with a representation alpha bar T of order 9. In fact, it will be a bit hard to construct the case where this is happening. You have to very, very carefully choose numbers. First row it is working more than, but the second row it failed. I will try to maybe same thing I have to do. Perhaps the same first row I should repeat. The first row. Well, at this position, yeah. I could have just done it like that. In which case, things would have been fine. 1 by 4, 1 by 4, 1 by 2 here. Things would have been fine. So now going to the second order Markov chain. So second order Markov chain would mean that for a first order Markov chain, if you want to find out the higher transaction probabilities, that means, say for example, I want to find out probability of transition from I to j in 2 steps. Or in the Chapman-Kolmogorov equation we have, from I it goes to some state k in the first step, so PAK, and then PKJ in the next step. This is how it is. Where k is an element of the state space of the Markov chain. But then this is what is called a 2-step transition, and therefore you can write the m-step transition probabilities Pij m, sigma k belonging to S. From I it goes to k in some L steps, and the remaining m minus L steps it goes from k to j, m minus L steps. But then when you look at the second order Markov chain, that's not what exactly mean by that. We have to have something different. So in the first order Markov chain, if you want to compute a probability whether the current state is enough to predict the state that is going to occupy at the end of the next transition. For example, that if xk or xn is a first order Markov chain, of course we have the initial probability vector, is a first order Markov chain. Then probability of xn plus 1 equal to an element belonging to the state space of the Markov chain given xn equal to k, the rest or I. Okay. Then xn minus 1, xn minus 2, all those things, or let us call it in minus 1, so on, x naught equal to I naught. All these elements of the state space of the Markov chain. Well, for a first order Markov chain, this is xn plus 1 equal to j given xn equal to I. So if this is the present, then future is just a future depends only on the present and not unaffected by any information prior to that. For second order Markov chain, this is not going to be the case. So come to the second order Markov chain. What you have is probability of, I want to predict xn plus 1. Now I have a state time n. So this is n minus 1, so on. Now I am here. For a second order Markov chain, information about this alone is not sufficient. I need information about this as well. So xn plus 1 equal to j given xn equal to I, xn minus 1 equal to I n minus 1, x naught equal to I naught. This is equal to xn plus 1 equal to j given xn equal to I, xn minus 1 equal to I n minus 1. So this additional information is also required for the second order Markov. So m order Markov chain would mean that starting from here we have to go m past things, including the present one. So that is the m order Markov chain. So now it is this sort of thing that I try to do, rather than the first order Markov chain. In that case, situation is now getting more complex. So I have to have the initial probability vector as in the earlier case, and not only that, because I am looking, I have to have the information of the second order. So in addition to having the initial probability vector alpha bar, so this is alpha 1, so on. If there are m states, so alpha m, and then I should also have, because I should know after the initially occupies such a state, what is going to happen after one transition. So I have to have a one-step transition probability matrix as well. So I call it just P1 to start with. So this is Pij, Ij varying from taking values from 1 to m. Ij taking values from 1 to m. So this one-step initial probability vector together with this, that will be going to give me the initial probability vector. Whereas in this case, it was just alpha bar. In the first order Markov chain case, it was just this alone that I needed to derive this distribution. Here what I need is this together with this, because initially it was occupying something like a state, any of these states, these respective probabilities. Now I require the one-step transition probability also, because look, I need two past information. Because in the long run what happens is if now I am at n plus 1, I should know not only this, I should have information about this. These two together alone will provide me that. And then I'll just try to give a typical example as well. And then the rest of the things, of course, this procedure can be adopted, but then interestingly, what happens is when you have some absorbing state, situation is now going to be different. Okay, so suppose now I go for a situation where this number of transient states is just equal to 1, and there is one absorbing state. We can go back to the prisoner's escape problem, but then that would be almost meaningless because there is only one cell and then he can escape through many of these things at the end of one transition. But then, assuming that he can stay back, he may not be able to move, then still there will be a probability of possibility of his staying back in the presence at the end of one transition, one unit of time. So, if there are only two states, then the possible state space for the second order Markov chain will be something like this, assuming that state 2 is absorbing. So this is absorbing state, and this is transient. So then what happens is, well, I had to just notice that I need something like this. I now write the transition probability like this, Pij. So this is the information about the current state. This is the one prior to that. That means something like xn equal to xn minus 1 equal to in minus 1. So xn equal to j, xn minus 1 equal to I. And now I have to say it is like state k that I am going to visit next. But then I will just introduce this as well for certain convenience. Pij jk would mean that now at the end of the n plus 1 the transition, I am occupying state k given that n minus 1 equal to say I and xn equal to j. So now if I write some L here with L different from j, suppose I write an L different from j, then this is going to be equal to 0. That is because this is just the previous, that current state at time n where we are in. So this, it is equal to j. So any L other than j will be giving a 0 value. Now this is the next n plus 1, at the end of the n plus 1 step where I am. Now this is actually standing for the state I am at time n. So these two things should be same, otherwise this is going to be equal to 0. So this is equal to, this is positive, this is equal to 0 for j, I call it L not equal to j, that would be more appropriate. L not equal to j. And for L equal to j, this can be possible. But then, if j is an absorbing state, then this k cannot be different from j either. Okay? So that is how the process is going. Now with this second order Markov chain, having defined the transition probabilities in this way, I don't know whether this is how I had not read any book on higher order Markov chains. I just stopped reading with, so far I have not read any book on higher order Markov chains, except that this is how the transition probability works, that I just intuitively calculated. I don't know whether this is a form that any author, any researcher gives for a second order Markov chain, transition probabilities. So with this as the definition for second order Markov chain, second order transition probabilities, I can now look at the infinitesimal generators corresponding to that, and then I have to say that these probabilities, well, if now k is the absorbing state, now if j is already an absorbing state, then what will happen is that this L has to be j and k has also to be equal to j. In order that, then this will be equal to 1. For the rest of the combinations, this is going to be 0. Just as in the case of the first order Markov chain, suppose m plus 1, I introduce a state like m plus 1, which is absorbing. Once in this state, it stays there forever. So from m+1, it cannot go to any other state. This is equal to 0 for I different from m+1. And this is positive. From some state, you need not have to necessarily say from 1 it can go to this. From some state, transient state I, it can go to this with positive probability. So that is essentially needed. So m, p, once in the absorbing state, it will not go to the transient state at all. So accordingly, if m+1 I write here, let's say for example j equal to m+1, the absorbing state of the second order Markov chain, then this will be m+1 and this also has to be m+1, otherwise it's going to be all equal to 0. All other combinations this will be equal to 0. But what I actually intended to do is, or rather wanted to present in detail, was how the phase time distribution will be looking like for this second order Markov chain. Well, of course, the derivation remains the same. And further what I wanted to do was, for a phase time distribution derived from a first order Markov chain, something like what we had done here, how it compares with a second order Markov chain for which the initial probability vector is this, and the first step transition probability, that means immediately after this, this is the one that will be coming into play. And then we have this law for second order transitions. Then how it will be looking like. That was the comparison actually that I wanted to make. The derivation would be essentially the same for the phase time distribution derived from second order Markov. But how it compares the first order Markov chain, the phase time distribution derived from a first order Markov chain with a transition probability that is like this, initial probability vector, this. And a second order Markov chain where we have the initial probability vector, this, but that will not be the complete initial probability vector. This also would be required. I have to plug in here to get the initial probability vector for the second order Markov chain. And then derive the phase time distribution corresponding to that. And then try to compare, for example, the mean, variance, or moments of order that would be possible. For one thing, a moment of SR not exist, for other things may not. Such questions, and of course, like as Professor Reinauer was telling, the coefficient of variation. That's in fact a very important squared coefficient of variation of order. That part I just want to do. Now, with that, I just conclude. Any question? Try to answer.
Thank you. Please feel free to ask questions. Do you have some?
There's some helpful comments that would help me in proceeding perhaps further.
So it's an ongoing research, yes?
Yeah.
Okay, and in this case, so in the first order use a matrix, but the second order...
Again you will get a matrix for the generator. Yeah, that I did not write the form. Because, see, there are certain combinations. You get a square matrix, transition probability matrix.
So still it is a matrix, but with a larger space.
Yeah, much larger.
Much larger.
Certain combinations, the transition probabilities will be 0. Essentially. Because it all depends upon, see, this J and
yeah, so it will be a sparse matrix.
It will be sparse matrix. And therefore, that this derivation, it's important that this T is non-singular.
Yeah.
There is every chance of the second order Markov chain finally you end up with a singular matrix. Therefore, it can happen that time till absorption is going to be infinity. If it is singular, non-singular, time till absorption is finite for a first order. But still, when you work with the higher order Markov chain, it may happen. I want to just identify the cases where it would be in non-singular, or rather singular. Yeah.
So let's take the speaker again. We have 5-minute short break just to do some technical preparation, then I will give a short introduction, and then after that,